And so then we also have an endothermic process from melting to freezing. So if we have water going from solid to liquid, we've got to break up that crystal structure, or at least the close associations. It may not be a perfect crystal. It might be an amorphous solid, but still they're very close to each other, and they're sort of stuck to each other. In a solid, the thing that characterizes a solid versus a liquid is that the atoms and molecules can't move past each other. So it's at low enough temperature that the intermolecular attractions have kind of locked it into a cage. Every molecule is in its own cage and it can't get out. It can shake around in that cage, which gives us the heat capacity for the solid, but it can't slide past. So you just give it 6,000 joules per mole of substance, and now it can slip past. It's still got hydrogen bonds, it's still got dipole-dipole interactions, it's still got dispersion forces. All substances have dispersion force attractions, and yet there's still enough energy now that they can slip past each other. What's surprising to me is that happens at a particular temperature, that there's a melting point, which, you know, this is the amount of energy at that melting point to get all of those associations broken to the point where they can slip past each other. So to go from solid to liquid, you sit at that temperature and you're just pumping joules in to those intermolecular attractions and allowing them to slip past each other. If you wanted to take things from the solid straight to the gas, that's sublimation. And so how much is it? Well, it's 46. It's all of those joules. So this is a nice area of science for those people who feel more like accountants. Okay, so just keeping track of the joules is more like accounting. And like I use these cash examples in your bank account, very similar. Tracking your joules is just accounting. If so many moles of a solid, you got to put 46,000 joules into that solid water to get it to go all the way to a gas. Okay. And then the reverse, those would be exothermic. And so that's why you don't want to put your hand over a steaming teapot because you've got vapor water and it's going to turn to liquid water because your hand is colder than the vapor, and it's exothermic. Those joules are going to go into your hand and give you a steam burn. So you don't want that. Same with liquid becoming solid, that's exothermic. So you got to suck the heat out of that liquid in order to get it to freeze. Pretty obvious stuff, but it takes, it's good to take the moment to talk about. So this is the same idea, but just drawn on an energy level diagram. So way at the bottom, you have the energy level of the solid, and then the intermediate, you have that energy level of, or energy state of the liquid, and then at the top you have the gas. And so that's what, down here you would have H2O solid, and gas. And so you can go straight from solid to gas with the sublimation, or the heat of fusion to turn it to a liquid, or heat of vaporization to turn it to a gas. And so everything should sum up. So you can take these intermediate reactions and add them together to get the total reaction. And so this is our standard enthalpies. So this is the definition, and it's really important. As you can see, I've underlined and bolded the words unmixed. Okay. So pure unmixed reactants in their standard states becoming pure unmixed products in their standard states. That's the definition of the standard reaction enthalpy. And most of the time, the mixing isn't a problem, except when you get to ionic solutions, okay, aqueous solutions, where you have cations and anions, because those intermolecular attractions are much stronger than hydrogen bonding or dipole moments or London dispersion forces. And so they can actually substantially change the heats of reaction. So if you were to ever mix concentrated hydrochloric acid with concentrated sodium hydroxide solution, it generates quite a bit of heat. In fact, just dilution, the mixing of like concentrated sulfuric acid in water, if you put that dilution enthalpy, I mean, the mixing generates so much heat it'll boil the water. And that's why you always put the concentrated acid into water, not the other way around. So if you pour water into concentrated sulfuric acid, that little small amount of water, when it mixes with the acid, will generate so much heat that it will reach the boiling point of that water, and it'll pop. it'll sizzle, it'll spray concentrated sulfuric acid on you. So you don't ever put water in the acid. You always put acid in the water. Okay. So you guys familiar with the Boston accent? You know, park the cob at a cub. Okay. So this is my phrase for that to help you remember: do as you oughta, add acid to water. You'll never forget it now, because that's a good way to remember it. You know, just remember from Boston: do as you oughta, add acid to water, and then you won't burn yourself. Okay, so this mixing is an issue, especially for aqueous solutions. So let's just take this generic reaction: 2A plus B gives 3C plus D, and then you've got the different standard molar enthalpies that you look up in the tables. And so you take, you know, the products minus reactants, so 3 times that standard enthalpy for C plus D, and then you subtract 2 times the enthalpy for A plus the enthalpy for B, and you get the delta reaction, the delta H for reaction. So products minus reactants. And you guys have already done this in the lab, because Tanner was asking me about some of the things with the Gaussian. So let's look at this. This is Hess's Law allows us to do this accounting business. So if we have reactants, and we have a situation where we've got reactants and products, and this is what we want to know. So that's our unknown. We can look up the reactants, we can look up the products, and what we're actually doing when we subtract the reactants is that we're tearing them apart. So this is the subtraction of the reactants to get to their elements and their standard states. And then this is the products. When we add together the products, we're getting that energy back and making the products. And if we don't get enough energy back to counteract the amount of energy it took to tear apart the reactants, then it's an endothermic reaction. But if we get more energy back by making the products, it's exothermic. And so this could be uphill or it could be downhill thermodynamically. And those elements are our standard states. So we would set this up here to be 0. So elements in their standard states at 298 and 1 bar. Those will be set to 0. So let's look at an example. So here we have the formation of ammonia. And elements in making ammonia would be hydrogen and nitrogen. So we'd have to think about what is the standard state for hydrogen at 298 Kelvin and 1 bar. It's going to be H2. You see what I mean by elements in their standard states? How does hydrogen exist at 1 atmosphere and 1 bar and 298? It's going to be a gas and it's going to be a diatomic. And same with nitrogen. It's going to be a gas and it's going to be a diatomic. So if you look up those in the table, the delta H of formation for those elements is going to be 0. So that's our 0 point. You can see that over on the left. Hydrogen and nitrogen are set at 0. Well, in order to make ammonia, we've got to break apart those. We've got to break apart the hydrogen and break apart the ammonia. So we take three halves of that hydrogen. Why do I want 3 halves? Because I want 3 hydrogen atoms, and they come in pairs. So essentially the halves part is breaking that hydrogen atom into 2, or molecule into 2. And so I've got 1 molecule of hydrogen. I'm going to divide that by 2. That gives me 1 atom. And then I'm going to multiply by 3 to get my 3 atoms. So 3 halves of an H2 gives me 3 atoms. And so I'm going to break that apart and get my 3 atoms of hydrogen. I'm going to take 1/2 a mole of nitrogen atoms, right? 1/2 of an N2 gives me 1 nitrogen atom. And so that costs energy. I'm breaking apart a single bond for the H2 and a triple bond for the nitrogen. So I would break those apart, and that would be the enthalpy of the nitrogen atom and the hydrogen times 3. So we could look those up in tables. Those are not going to be 0. N atom is not 0, and H atom is not 0. So we can find those, add those together, and that's where that level would be at the top. Then we can find the amount of energy generated by making 1 NH bond. And that would be this one. So we've made an NH bond, we get 314 kilojoules. We make another H bond, we get 390. We make the third H bond, we get 466 kilojoules. And so then we can add all of this up, and we get the change, it's exothermic, of 45.9 kilojoules. So this is kind of Hess's law in action. We can build this molecule one at a time, or we could look up ammonia and see what its formation enthalpy is. So you can use these tables to build up the different molecules. What if we really wanted to just make NH2? Just that strange molecule NH2, or maybe a diatomic of NH. I mean, it exists, right? Well, this would be the delta H for NH. If we subtract the 2H from that, then it might come down some. But the point is, this would be the difference to get that NH from a nitrogen. Okay, and so we could figure that out and use Hess's law to get the difference. Now, this is using the tables. This is how you would do thermochemistry using the thermodynamic tables. But what about Gaussian? Gaussian has a different 0 point. So Gaussian doesn't know about elements in their standard states. To do that, you'd have to calculate the enthalpy of all the elements. Okay. But Gaussian does know about particles like protons and electrons and so on, and nuclei. And so you could put all of the electrons, you can calculate the energy of a nucleus, you can calculate the energy of the electrons. And so this is the 0 point for Gaussian. It's way at the top. It's all nuclei and all electrons separated to near infinite distance. So if you pull all the electrons off of all the nuclei. Now what's interesting about that is you say, well, that's an unrealistic state, but no, that's a great state to have for a computational program, because that's definable for every substance. Every substance can be made out of nuclei and electrons. Okay, and that's also so far uphill that everything conceivable in nature is going to be downhill from that. So every energy in Gaussian is going to be negative, because look how high up 0 is. Even if you make hydrogen atom, you've taken one proton and one electron and gotten them close together, and that drops down half a Hartree. Okay. So because this has a different 0 point, we're going to have much different numbers. And so if we take this 0 point and we calculate the energy of the hydrogen atom, then that's this energy. And if we calculate the energy of a nitrogen atom, that's that energy. You see, it's much more negative, because we've taken 7 protons that are in a nucleus and we've added 7 electrons. So we've really dropped down a lot, 107 Hartrees. And if we bond a hydrogen together, we get 1.16. Multiply that by 3 because of the 3 hydrogens, and we get the 3 hydrogen atoms plus a nitrogen atom. And then over here, we just compute an ammonia molecule. So we put that into Gaussian, build it, calculate it, and it drops down negative 113 Hartrees. Converting those to kilojoules, we have these huge amounts. Negative 296, 685, and this is negative 296, 639. And so we take the difference in these numbers, products minus reactants, and we get that delta H. Okay. So it's same thing in Gaussian. We just don't have to do the intermediate steps. Now we could do those intermediate steps. We could calculate the NH molecule for Gaussian and get that difference, and the NH2 and get that one, and then the NH3. And so we could map this out in Gaussian, because the Gaussian 0 point is way at the top, and it'd be pretty easy to do. And so this is similar to what we were just talking about. The standard enthalpy of formation is that reaction enthalpy for the formation of that compound from the elements in the reference states. So what we just showed on the previous slide was the standard enthalpy of formation for ammonia, negative 45.9 kilojoules. And so the formation enthalpy for the elements is 0, and so all the other compounds made from those elements is non-zero. What we're going to do in the calorimetry lab is we're going to work with combustion enthalpies. So we're going to measure the enthalpy of combustion. which is a substance, a fuel reacting with oxygen to make CO2 and water. We want to make sure that that reaction goes to completion. So we're going to have excess oxygen. That doesn't change our thermodynamics because oxygen is an element at standard state. So we can flood the system with oxygen and we're not adding any entropy. So we just put that fuel in with excess oxygen and then we see how much heat was generated. And we know the enthalpy of formation for water and for CO2. And so we just have one unknown. We have that enthalpy of formation for the fuel. And so this, we can measure the combustion enthalpy and we can calculate this. So this right here is the value that we don't know, and we measure this, experimental. And we know the delta H of formation for water and for CO2. And so we'll put in the fuel, we'll burn it in excess oxygen, we'll look at how many joules comes out, and then we can put it into this equation and solve for the delta H of formation for that fuel. Okay. Now let's think about calorimetry. This is the simplest calorimetry experiment that you can do. It's just hot and cold water. And for some reason, people make it way more complicated than it needs to be. Okay, so you just take the energy in hot water and mix it with cold water, and it comes to an average temperature. And so I've tried to make some diagrams for you. On the y-axis is the temperature, and on the x-axis is the mass. And so we have a total mass of water that we're going to mix. So this is the smaller mass of hot water, mass of hot, and this is the total mass. And then this is the temperature of the hot water, this is the temperature of the cold water. So you can kind of think of this as this amount of water here has got excess joules, and this amount of water is the cold water. You mix them together, you get this total. And so essentially the heat's going to flow into the total mass. And so let's talk about this for a second. So the first law, we're negating the heat flow out of the system. I mean, you know, capturing the system and the surroundings, so the total heat change is zero. And so you can rearrange this. Change the sign on one of those and they equal the other because they're equal in magnitude, opposite sign. And the surroundings in this situation are water and calorimetry parts. So we're bringing in excess heat with the hot and then it's delivered to the whole. So we can look at this and think of it in terms of the system delivering heat to the water and to the calorimeter parts. The calorimeter parts are the glass dewar, okay, stir stick. There's a impeller in there, a little propeller that's stirring the water, and then the thermometer, okay. And so what we predict for the temperature isn't going to be exactly accurate because we're going to have heat lost to the calorimeter parts. And so I've tried to color code this. We have this heat flowing into the calorimeter is equal to the difference between that the heat system and the heat in the water. And so this is a picture of what's going to happen. The temperature is going to drop, and the theoretical temperature, if these were equal masses, should be halfway up, right? Because it's equal masses. If I have, let's just think of it as in terms of 100 joules of excess heat in the hot water, and then mixing it with cold water, it's got 50 joules. Then it's going to reach the equilibrium point in between at 75 joules. Okay, if I have equal masses. And so you can keep track of the joules that way. And in fact, that's a way to do this. If you're just dealing with the water alone, it's just the weighted average of the masses. So if I have a 50-50 mixture, that temperature is going to go halfway between the two temperatures. Okay. So here we have the total mass of the system, and the temperature has come down a little bit lower than the theoretical. So there's an actual temperature here that's lower than the theoretical. And it's lower because we've warmed up the calorimeter glass, we've warmed up the metal in the thermometer, we've warmed up the stirring stick. And so those things have stolen some of our joules. And we have to account for that. That's the calorimeter parts. And we'll have what we call a calorimeter constant. So we put in a certain amount of joules, and it takes a few joules to raise the temperature of the calorimeter parts, and the rest of those joules goes into water and raises the temperature of the water. We conceptually have what's going on. And so we can calculate the heat released from the system. So how much hot water did we have? It's going to come down to the final temperature. Okay. And if we take all of that excess heat, so we have the cold temperature and then we have the hot temperature. And that difference is the excess heat. And so we can do this conceptually. We can say, let's take all that excess heat out of the hot water and bring it down to the cold water temperature and set those joules aside. How many joules is that? Well, it's the difference in the temperatures times the heat capacity for water times the mass. Okay. So up here, this is our toolbox. We're going to just work in grams for this. So we're using the specific heat of water. 4.186 joules per gram Kelvin. We've got the temperature differential, T cold minus T hot, and why is the T cold over here? That's the final, right? Final minus initial. So this is going to be a negative number. The calorimeter, the specific heat for water and the mass of the hot water. And so that will give us a negative number, and that's the joules that we pull out of the hot water. And we can set those aside. Again, this is a nice thing about accounting and keeping track of our joules is we can calculate those joules and set them aside and label that Q system. And then the surroundings are all the water and the calorimeter parts. So we're going to take those excess joules out, and then we're going to look at the total amount of water and the calorimeter, and we're going to put those joules into this total system. You see mentally what we're doing. We've got cold water, we add some hot water, and so we're saying that mass of hot water has a certain amount of excess joules in it, and the excess joules are from the cold temperature to the hot temperature. How much hotter is it? We take that difference in temperature and pull those joules out, set them aside. Then we allow the water to mix. We have a total mass of water now and the calorimeter parts, and then we put those joules back in, and it warms them up. Okay. So now the heat captured by the water. We have this total mass of water now, okay, and it went from the cold temperature up to the final temperature. Okay. And so how many joules was that? So T final minus T cold, that's a positive difference. We have the specific heat of water, it's a positive number. We have the mass of the total, positive number. And so this is a positive amount of joules that went into the cold water and raised it to T final. Okay. And so that's the joules. So we have our joules that we got from the hot water now. We'll put them into the cold water, see how many joules that adds up to. It's not going to be exactly the same number, and so the other joules went into the calorimeter. And so the calorimeter constant is an unknown amount. We know the specific heat of water. We know CH2O. So I'm going to put a check mark on that one and a check mark on that one, but this one's a question mark. Okay, because how many joules does it take to raise the stir stick a degree? Who knows, right? And so that's why we do this. We do this so we can understand how much temperature is going to be stolen, how many joules are going to be stolen by our stir stick and the glass and the thermometer metal and those things. Okay. And so what we really need to know is what's the difference between the heat that was delivered from the hot water and the amount it took to raise the cold water to the final temperature. That difference in joules is how much went into the calorimeter. And how much temperature did the calorimeter change? The stir stick, the glass, the thermometer went from T cold up to T actual. Because it was in equilibrium with the cold water before we added the hot water. And so it went from TC to T actual. And so we want to take the difference in joules of the system and the cold water, or the system and the water, and divide that by the temperature change, and that gives us the calorimeter constant, because that was our unknown in this equation. So this is a valuable piece of information that tells us something about our measurement device. It tells us how many joules are going to leak out when we do an experiment. There's one other thing that's not captured by any of these calculations, and so there is a source of error in all of these, and that's evaporation. So we're losing hot molecules all the time, okay? And so your numbers are going to be off a little bit because of evaporation. Okay? It shouldn't be, but just a few percent. So if your numbers are off like 50% or whatever, then it's not evaporation. Okay? Unless you're working with pentane instead of water. So it's just accounting. But you can see how with all these Q system, Q water, Q calorimeter, you can take a very simple thing of mixing hot water and cold water and make it overly complicated. But I've tried to make it as simple as possible. So keep coming back to this example when you get to lab and make sure you understand this one before you go on and try to do bomb calorimetry. Because if you can't keep track of your joules here, then forget about using enthalpy of combustion and heats of formation and benzoic acid we're going to calibrate it with, and so on. So let's look now at the enthalpy of combustion experiment. So here's with all the numbers put in there, what Q-sys is and what Q-water is, and so there you have all your knowns. You have every one of these variables in your experiment. You got TC, T actual, mass of total, mass of hot, the specific heat of water, and so you can calculate the calorimeter constant from those measurements. The one thing that you measure that's not immediately obvious is this T actual, what the final actual temperature is. And so that determines everything. So now let's think about bomb calorimetry. The main thing that changes here is not that we're adding hot water. We're adding enthalpy of combustion. So we're putting in a known, a benzoic acid tablet, and we're burning it. So we weigh that tablet, and because it's a standard and it's pure benzoic acid, we know the delta H of combustion for benzoic acid. So if you know the mass, you know how many joules are going to come out of that bomb. So we carefully weigh that tablet, put it in there, wire up the bomb, put in excess oxygen, seal it up, stick it in the cold water in the door, get the stir going, and plug in the electrodes, make sure the data collection's going, it's collecting temperature, and you say, okay, ignite the bomb, punch the button, nothing happens. I always wanted a boom or something, but no, it's just a light comes on. And so it's this kind of anticlimactic, but that's good. We don't want climactic events in the chemistry department. So you punch the button, a light comes on, and then you see the temperature start to creep up. Yeah, and so that's all the excitement you're going to get, is that this temperature doesn't change, but in the 4th decimal place, and it's doing nothing, and then all of a sudden it changes by a half a degree, a whole degree, a half a degree, and it starts to taper off, and you're like, it worked, And then you have the real excitement of opening up the bomb to make sure it was complete combustion. And so you open up the bomb, you break the seal, and you hear, there's a little bit excess, like CO2 and some oxygen that comes out. And then you open up the bomb, and you want to see a nice, wet, clean interior, because it turned into CO2 and water. Okay. And sometimes you open it up, and it looks like the tailpipe of a diesel truck. Which is incomplete combustion, or you didn't get enough oxygen in there, and it's just completely caked with soot. Okay. So the oxygen burned what it could, but left behind a whole bunch of black soot. And so we'll have an ultrasonic cleaner up there, and you can clean out that bomb and start over. Okay. So everybody needs to have 2 good runs, and so prepare yourself. So that's the enthalpy of combustion for the benzoic acid. And we'll use that to get our kcal. So it's the same, essentially, it's the same treatment, but now at the bottom we have the fuel, mass of the fuel, the heat of combustion. So instead of the hot water delivering our joules, the benzoic acid will deliver our joules. And then we'll get the calorimeter constant that we'll use for the unknown fuel. So we can put an unknown in there and calculate the enthalpy of formation. Any questions on this? Okay. And so once we have that calorimeter constant, the surroundings and the water are known, and then we can calculate. We can use that calorimeter constant down here to calculate the heat generated by the unknown. And so we weigh out the unknown, we put it in, we burn it, and because we know the mass, we use this to calculate the joules, and so we have joules per gram. Now, if it's a pure substance, and we know the molar mass, we can get joules per mole. We can get enthalpy of combustion. If it's not a pure substance, let's say it's a food item, like a carbohydrate, like sugar or some sort of protein or some sort of fat, then we could calculate the joules per gram and check the label. And so sometimes students will do food. We've had students do gummy bears. We've had students do Fritos, chicharrones. We've done all these different things. But I like to stay away from the oily stuff like Fritos and things, because when you press the pellet, the oil comes out. And that's instructive in itself. Because you squeeze the grease out of Fritos, there's a lot of grease still in that cornmeal. So we'll stick to maybe like a flour. You can have a high protein flour, a low protein flour, things like that, where you're just getting calories per gram. And you can see that that's where these nutritional values come from, that the difference in calories per gram for the wheat, or carbohydrate, or starches, you'll get those measurements right off of this instrument. Okay. Yeah, so that's pretty nice. So then we have these standard enthalpies of formation, and we can tabulate them. And so here's an example of just a few. So we've got some fun ones on here. We've got water, negative 285.83. So just think about that number. What is that telling us? That water's enthalpy of formation is negative 285. So you tell me, this is the interactive part of the day, you tell me what you can draw out of that number. And if you want to compare it to some of the other numbers, that's fine too.
Well, since it's negative, it's exothermic.
Exothermic compared to what?
Compared to, like,
Yeah, so that's a good, but you're right, it is exothermic. But look at that word formation. This is a table of the standard enthalpies of formation. So that word's very important.
Compared to its reactants?
Yeah, that's right too. And so what are the reactants in the enthalpy of formation?
The elements, H2.
The elements in their standard states. So all three of you have a piece of it. It's exothermic relative to the standard states, the elements. Yeah. So you put those together, and so this is hydrogen mixing with oxygen, reacting to form water, is exothermic. We know that, right? I mean, that's how we got the space shuttle into space, is mixing hydrogen and oxygen. That's why that big tank was on the front. It had hydrogen and oxygen liquid and sprayed into the main rockets on the space shuttle. And that generated, I think it was like 75% of the thrust. It has big old solid rocket boosters on the side. They were only giving it about 25%. Yeah. It's unbelievable. Hydrogen and oxygen really does give you a lot of energy. So if we take this exothermic hydrogen and oxygen and mix it together, we get a boom, right? Expanding gas. We don't get the liquid water. We get most of the vapor. But look at this little explosion, right? That's not going to be very good for a rocket. But we know geometry. Okay, so we could put that at the focal point of a parabola. And so then all of these vectors are going to come out of that parabola collinear. I mean, not collinear, collimated. Even that one. And so then this shape is what we see on those rocket motors. Because it's taking that symmetric explosion and taking all the force and directing it in one direction. Okay. And so it's this unequal force. It's hitting that parabola, and there's a force going up from the deflection of those hot gases. And so that's what propels it forward. Okay. And so this is rocket science. Yeah, whenever you say, it's not rocket science. Well, this is actually. So you can take these enthalpies of formation and you can calculate the different exothermicities, and that would go right into the velocity of those gases. So the more exothermic it is, the more kinetic energy those exiting gases are going to have. And so here's some other ones: hydrazine rocket fuel, where we could take hydrazine liquid, because liquid hydrogen, boy, what a pain that is. It's really low temperatures. So let's get away from liquid hydrogen and use hydrazine. So here's N2H4 liquid mixing with oxygen. So let's calculate this one. It's making ammonia and water. So we could go back and we could calculate those values. And essentially we have the products minus reactants. And so we have 2 times of this number here. So negative 285. Okay. And then the hydrazine is plus 50. And we're going to be subtracting that number. So 2 times 85. Someone calculate that for me, would you? It's close to 300. Okay. So that'd be negative 600 plus another negative 50. Okay. So negative 650. And so then probably I overestimated the water, so by about 15 each, so that's 30, so I come back down to 620. That would be an estimate. What do y'all get?
Yeah, negative 571.
571, okay. So this is negative 571. Pretty good. What'd you get? Oh, I thought you had a comment. Okay, so it's even better. Okay, so the water, hydrogen and oxygen making water was 285. This is negative 571. Fantastic. Okay, but oxygen, man, that's a pain too. In terms of gas, cryogenic oxygen. So then they started thinking about rockets with hydrazine and hydrogen peroxide. Now, hydrogen peroxide is pretty dangerous, pure state. So it's you're not really helping yourself too much by going to hydrogen peroxide. But it's still, if you can handle liquid oxygen, you can handle liquid hydrogen peroxide, and you don't have to have the cryogenics. And so I've got these numbers here just to save us some time, and these are. Right here, negative 818 for the hydrogen peroxide, hydrazine and hydrogen peroxide, negative 800. And so that's quite good. And we have 2 liquid, a liquid fuel and a liquid oxygen. But hydrazine, if you look at it, it's plus 50. And so it's uphill from the elements. And so we just take hydrazine by itself and give it a little push. What kind of push? Maybe a spark. And so you can have a little hot wire or a spark and just push hydrazine by it and it'll decompose because it's uphill from nitrogen and hydrogen. So you can just take hydrazine and give it a spark and it'll spit out hot gas. It's not great, 50 kilojoules per mole, but no oxygen needed, no oxidant or anything like that. And so that's what our little boosters use, through the adjustment of spaceships, the pitch and yaw and so on, use these little hydrazine boosters. And so we just have a little reservoir of hydrazine and a little sparker, and you pump it out and it sprays and pushes. And so it really is rocket science. We've got a few seconds here that I can show you a video of that if you've ever seen that. Did I show the MDA, the Missile Defense Agency's kill vehicle last semester? Yeah, does this ring a bell? Okay, so let's look at that. Let's go to YouTube. Here we go with speed, the lack of speed. Sounds pretty dramatic. Kill vehicle. What is it talking about? While this is loading, I'll tell you what this is. So the Missile Defense Agency is a research arm of the Defense Department that's coming up with ways to kill intercontinental ballistic missiles in space. And so this is an example of a test. So this thing has gyroscopes inside, a computer. It's basically a big rock that gets in the way of a missile. And so if it hits in space, it just destroys it, and it's not going to do what it's supposed to do. But you've got to position it very carefully. And so it has these hydrazine rockets. Well, it's mainly meant to position itself in space where there's not a lot of gravity, but they have enough juice in these things that they can hover. And so it can move around and track. Now we need to use the hydrazine because a propeller like a drone is not going to do you any good in space because there's no gas to push with the propeller. So you need to use rockets. Okay, so we're used to seeing drones now. This was much more interesting before we had all these quadcopters running around. Come on. So they have this in this test facility, and they've got it in a big cage in case the software doesn't work. Right? Because what if it's not in control? It's going to hit something and hurt it. It's resolving host.
I always did wonder if we had anything like that.
Yeah.
For safety reasons. And with all that.
Yeah, so you can kind of see the preview there.
Can you look at the preview, not the video?
Yeah. Let me try this one.
Just email us the video.
Yeah, I can put it on Blackboard. It's pretty amazing. And so we can do the same thing with Gibbs Energy. I'll put that link on Blackboard. We can do the same thing with Gibbs Energy and get spontaneity of the reaction. And y'all did that again in the lab as well. Same definition essentially. So now we have that full thermodynamic table. So we have the entropy, standard entropies. We have the enthalpies and the Gibbs energies. The enthalpies and Gibbs energies have a different reference point than the entropies. Entropies is absolute zero, but the reference point for enthalpy and Gibbs energy is elements in their standard states. And so you can see that on these rows that have pure elements like oxygen, O2, 0, 0, and 205. So the 205 is the standard entropy for the oxygen. Also notice that O atom is not 0. Okay, and it's positive, so it's way uphill from O2. So it takes that many joules to break apart an O2 molecule. What's that? Oh, you can hear it. Yeah, it's probably playing in the background. No, thanks. Yes. So, yeah. So. Yeah, there it goes. So that's hovering around. You can see it adjusting. The one on the bottom is firing so frequently because it's going against gravity. But the others, it's moving left and right and managing the tilt as well. So that would scare me pretty bad if that was coming down the hallway. But again, it's not a kill vehicle for killing people. It's actually to prevent that. It's to get up in space and get in the way of an intercontinental ballistic missile to knock it out of the sky. So it's interesting, and this is a pretty old video, so they've had this for a while. All right.
Do you know how big it is?
Yeah, I think there's like there would be multiple ones on a rocket, so they're about this big.
Okay.
Yeah. And of course they may have different versions of it now.